right? Talking about something that I introduced already for those of you doing the electronics course with me. Some of you all will have come across this if you have done the course signals before. Then you know what we're talking about. But in electronics, we came across it when we were talking about the response of some filters last time. Okay, so and I told you that we'll do it more formally here. So we're going to talk about this, and this is one of the big properties that we make use of in the Fourier transform to again to allow us to predict what the frequency response of a system should be without having to go back in time and or solve the thing in frequency and plug in values of omega and see what the magnitude of the response looks like. Right? So if you have a system here, so I am giving you a transfer function here, however it came about, and I want to figure out, well, what is the magnitude versus frequency response of this, and what is the phase versus frequency response for this. So, I mean, you could do it the hard way or you could do it the easy way. The first thing that we do is, of course, if I'm asking you, let me go back here, to figure out what is the frequency response for this, then you're talking about the frequency domain. So somewhere along the road, I'm going to take S and I'm going to replace it with J omega. Right? Remember the J inside of here. So the approach that we take now, we substitute S equal to J omega in here. Easier to do if you get rid of all of the higher powered factors. So the first thing that you do, if you're given a quadratic like this, try to factorize it, right? So because I could have just done it here, and if I were to substitute S equal to J omega, just as it is here, I would have 40 J omega over J omega squared plus 14 J omega plus 40. It's 40, right? I wrote over my own writing. But then I need to factorize something afterwards, which is what we are about. So it's easier to factorize with S than to factorize J omega all squared. So if you're given the transfer function, factorize it first if you can. That's step one. So if you factorize it and then make the substitution, this is what J omega is going to be. And then we're going to do something now, which is to draw something called an asymptotic Bode. I pronounce it all sorts of ways, but down in our neck of the woods, everybody in campus and everybody who's ever done control systems and signals calls it Bode, right? I'm not too sure how Henry himself pronounced it. He was, the name is Dutch, so I think it's Bode. I believe I've heard somewhere else, but anyway. So once you have the response down to this point, of course, I could, the sort of hard and fast way for this now is to pick a set of values for this, starting omega equal to naught, which is DC, and I could go plug omega equal to 10, omega equal to 100, omega equal to 200, 500, etc., etc. And every time I do that in here, plot the magnitude, because if I plot omega in there, this is a complex number, so I'm going to have to plot the magnitude of J omega, work out that, and then on the complex number now, work out the argument of it, so I get a phase, right? Yeah, you could do that. That's fine if you have time, or you could use MATLAB and so on, for instance. Or what he came up with was a way of sketching the frequency response. And that sketch allows us, again, like we've said, in using the Laplace transform and in using all the transforms, you want to go from a zone where it is easy, sorry, where the manipulation is tedious or time consuming. You use the transforms to carry you from that universe into another universe where the manipulation is easy, it's just arithmetic, or in this case, is going to be drawing lines. And depending on how the lines intersect and connect, you're going to be able to see in a general form how the response in frequency of the system is going to be, right? So out of this thing, Henry Bode, he was a telecommunications engineer, and telecoms people, of course, are always greatly interested in the frequency response of systems, the bandwidth of systems. So you can imagine if you're dealing with things that go from very low frequencies to very high frequencies, how tedious it would be if you have to go back to something like this and plug in all those omega values to see, because they really don't know what the response is going to be. They're going to have to go from very low to very high, and every time you calculate, you're dealing with a complex answer. So he came up with this thing, and out of his plot, out of his technique, you get two plots. You get a magnitude plot, which is the gain plot, and then you get a phase plot. And these are the sort of what we're going through here, and already you met some of those last time in filters, is that you're going to come up with asymptotic plots, which are, this is just another word for straight line. Right, so straight line frequency response plots. The other thing is that the magnitude plot is plotted on a log scale. The amplitude of the y-axis is in decibels, right? And we saw a decibel is 20 log to the base 10 of a value. Okay? Really and truly, the value is, this is really supposed to be technically a ratio, right? But if you want, it's technically v, whatever the value is, over 1, and log of 1 is 0 when you simplify it out. So it doesn't complicate matters. But the decibel, to convert a raw number to a decibel, is 20 log to the base 10. That particular base 10 thing cost me about 2 days of work. There was some work I was doing when I was studying, and I had to convert the values to decibels, and like yourselves, they gave me MATLAB to work with. And the MATLAB answer kept being, when I calculated with a calculator, getting one thing, and the MATLAB answer kept giving me the wrong values all the time, until I realized after 2 days of trying to figure it out, that at that point in time, if I wrote the log function in MATLAB, this was giving me the log to the base e, whereas it's supposed to be log to the base 10. Right? They've clarified it now, so you I think you have a log 10 and so on in MATLAB. So you have to be careful what you're doing in it, and these are the kind of things that could give you headaches and nightmares. So you know, your calculator telling you one thing, MATLAB telling you the other thing, and you can't figure it out. But eventually it dawned on me, right, that it was doing it to the wrong base, right? So these things happen. So the first thing is tears, literally, right? So the magnitude, the amplitude is in decibels, and then, as we discussed before, the frequency range is also a log frequency range, right? Which means it's in powers of 10. So if you look at it here, this is 1, this is 10, this is 100, this is 1,000, 10,000. We could go all the way up. The business about it is that being a log scale, we can compress, as you see right here, you can compress, in this case, 10 kilohertz into a fairly small diagram. All right, it is for illustration purposes. So the actual, in many cases, you're not concerned, like if the value, if you look at these values here on the graph, you're going to see, like, for instance, this is 1K, this is 2K here. All right, so you can estimate 1500, 1.5K will be somewhere in the middle here. As I go on a little thing, this is 2 here, this is 3, this is 4, and so on. It starts to get a little more compressed. So like when you reach, if I want you to, on this graph, for instance, that you had 8K for instance, to plot, it's going to be a little bit, sorry, not even 8K. If you had something like 7.5K, you can't really distinguish between 7 and 8K here. So it isn't intended to be like that, right? And what you would do is if you draw whatever it is, that you would indicate a particular frequency point that you can't really pick off of the axis, all right? But the idea is to be indicative, to show you what is expected rather than plotting exact values. And the same thing goes for the phase plot. The phase angle here is in degrees. So they plot it, it starts the middle, so it goes plus and minus, and it increments depending. And they use the same frequency axis, the same log frequency axis, because typically what they do with the Bode plot is that you have the two diagrams, one on top of the other, right? So you have the magnitude plot on top, and you have the phase plot below, but they share the same frequency response, frequency axis, sorry. So that once you see a frequency behavior in the phase plot, you could just go straight upstairs and you could see what the magnitude at that frequency is looking like. Yeah? Just some simple rules here. So decibels and log magnitude scales. All right, and that decibel thing is actually going to make it easy for us to do certain things as we go along. All right, so just quickly, we have a shorter while we can knock off this here. If HS, if the frequency, sorry, a system has a constant transfer function, so HS is a constant, 2, 100, 75, that kind of thing, right? What is the magnitude versus frequency? Well, of course, this is not frequency dependent, so that the magnitude of the frequency response for it is going to be a constant, right? Whatever that value is, the magnitude of K. It's a number, so the omega is just going to be a constant, right? And the phase, of course, if the constant is positive, the phase is 0. If the constant is negative, negative is minus 180 degrees. In terms of degrees, is the opposite direction. So if HS is a constant, then the Bode plot, as you see, you transform it into the log scale in decibels. So if H j omega is a constant K, then it's going to be 20 log of K, whatever that happens to be in decibels. So you plot it out, and this is what the magnitude plot is going to look like. A constant for all frequencies, because that's what the HS is. And the phase, if K is positive, then the phase plot is 0 for all frequencies. And if K happens to be negative, then the magnitude, sorry, the phase plot is going to be minus 180 degrees. Yeah? Then the other one, which is kind of where we introduced this in filters before, what about a system that has a pole at the origin? So our transfer function looks like K over S. So this particular transfer function, if you plot it on the S plane, this is a pole at S equal to 0. No imaginary parts, no real parts. It's right at 0. So what is the magnitude and phase response? Well, the first thing, you plug S equal to j omega into it, so that the magnitude is going to be the magnitude the magnitude response is going to be the magnitude of this, right? Which is, if you look at that as a complex number, 1 over j. So the magnitude of that is K over omega, and the phase is minus j, which is minus 90. So look at this bit here, right? And that'll be the last thing that we'll look at today. If I take this bit, which is the magnitude plot, convert that to decibels, it's 20 log K over omega is 10 K over omega, right? Which is 20 log K minus 20 log omega. Yeah? So if you put that now on a line, put that on my, what do you call it, on my log scale, 20 log k minus 20 log omega. Well, let's take some points at that point so we can see what it is. If omega is 1, when omega is 1, 20 log of 1 is 0, right? So when omega is 1, the line is at 20 log k. When omega is equal to k, then the line crosses 0, right? So that the line goes like this. And at any point in here, that point is 20 log, well, this is a shorthand, 20 log k over omega. And what is the slope? We did that little derivation by looking at an actual response in the what do you call it, in the when we're talking about filters, right? But let's derive it here. We said we would prove it formally. If you look at this now, right, when omega is 1, 8 omega is 20 log k. That was here, right? So when omega is 1, the magnitude of h omega is 20 log k. When omega is 10, let's grab here now. When omega is 10, then the slope is 20 log k minus 20. Right? Because if omega is 10, here, this will be 20 log k minus 20 log of 10, which is, well, log of 10 is 1. So that's going to be 20 log 10 minus 20. So this point, if we were just to substitute and call this 10 for argument's sake, then this is 20 log k minus 20. So in other words, over this change here, this dropped by minus 20 decibels. And we said that a change of a frequency of 10, a multiple of 10, so 1 to 10 is what we call a decade. One frequency is 10 times the other, then the next decade up would be 100. So you can see why we plot the log. By using our log scale, we could plot in decades very easily, so that a single pole at the origin, the frequency response decreases at minus 20 decibels per decade. Yeah? Right here. So a single frequency, a single pole at the origin, the gradient, the frequency response, as you crank up the frequency, it decreases at 20 dB per decade. A single pole, for instance, is a capacitor. So if I have a capacitor, who has a big capacitor? But if I have a capacitor and I have a signal going through the capacitor here, and you're looking at the voltage across here, we saw already at DC at very low frequencies, the capacitor is largely an open circuit, so that the voltage here is going to be whatever is that source. As the frequency starts to crank up, the capacitor slowly starts to short circuit the voltage, because the impedance of the capacitor decreases as frequency goes up, so that this voltage now is going to progressively short, and the voltage here is going to get less and less. Well, as we're seeing in the frequency domain, that response is going to look like this. It's going to decrease. So as the frequency goes up, the magnitude of the response, right, is going to drop. And it's going to drop at 20 dB per decade. It looks nice and linear. When you draw the log scale, everything is a nice linear slope. We know in the time domain that the response is an exponential kind of decrease. All right. And what about the phase? Well, the phase response, so the magnitude response is going to look like that. What about a phase? Well, Hj omega is minus, remember, it is K over J omega, so that the phase is a minus J, which is minus 90 degrees. So that a pole at the origin, the frequency response decreases in the log scale at a minus 20 dB per decade, linearly all the way down, and the phase is minus 90. So it's always minus 90 degrees out of phase with whatever signal was driving it. Yeah? Fair enough? So any questions before we close off here? Right, so you understand the concept, what we're doing. So just quickly again, you notice what has happened. You're given Hs is equal to K over S. The question was, what is the frequency response of that? Well, yeah, I could go and I could find the inverse thing and plot it in time versus frequency and all that kind of thing, right? Or I could plug S equal to J omega here and I could plug in all the omegas and so on. But we're now seeing that something like a single pole at the origin, that the frequency response now is a linear, well, this axis didn't plot good, but it's a linear frequency response. It starts high at close to DC and it continues decreasing all the way down as you increase the frequency. And that the phase is now a constant minus 90 degrees. Right, so that you have a behavior here without solving the thing. Here's a line that is showing me, so I could get a visualization now that as the frequency goes up, the magnitude of that response is going to drop. All right. So we'll continue this as we go forward, because we have all other combinations up to and including quadratic responses to look at as we go forward. All right. So look over the notes and listen to this when you get a chance. And tomorrow, please God, we will continue with this. All right?